a little bit about me first. I'm a developer since a long time ago. When I was 10 years old, I started working on QBasic and BASIC for Commodore. Then I worked in Visual Basic, C#, .NET, JavaScript, you name it, all that kind of stuff. After 8 years doing that, I switched to functional programming. I let all that object-oriented world aside, and I did my thesis project in Haskell. And I found Erlang and started working in a company in Argentina called Novamens. After a year there, I moved to Inaca. And in Inaca, we are basically a company that builds end-to-end applications with iOS clients, Erlang servers for them, and Ruby for the admin tools. My part in that, as you can guess, is the Erlang backend. Today, I will talk about how do we scale web projects that have an HTTP API and a component that keeps clients connected to the server for long periods of time. It seems to be a narrow scope, but we found that it's a design pattern we use in a lot of systems. Almost every iOS application we have has a socket that connects to the server to receive real-time updates, and also has an HTTP API to deal with it. The HTTP API lets you connect with other systems and be independent of how it's implemented. And the socket it provides optimal way to connect because it lets you send small pieces of data through TCP without the burden of other things around. Samples of these applications are, for instance, chat rooms, social sites where you get updated of what's going on in your network, or my favorite one, sports sites, when, for instance, there is a game going on somewhere and you get updated of what's happening there. OK. And what will we do with these kind of sites today is we will try to optimize the way we use OTP behaviors, TCP and HTTP connections, and we will tweak a little bit the underlying system configurations. You will see in a while. What we will not deal in this talk is we will scratch the surface, but we won't go in deeper detail on how to handle multiple nodes on machines, or which databases you should choose for the different projects you have. To show you the process of scaling an Erlang web server, I will present to you a sample application. As you can guess, since I'm Argentinian, it will be about soccer, of course. In this application, the general idea is like a soccer match is being played somewhere, but you are working, so you cannot be at the stadium. And then you want to get the updates of what's going on there because you're a fan of one of the teams. There is a reporter in the stadium with a device. He can tell you what's going on, so you need a system that connects you to him. This system basically receives a stream of events from the reporter and broadcasts them to tons of users that are connected to it. The basic requirements for this kind of system is there are many concurrent users using the system at the same time, and they all connect at the same moment, at the beginning of the match. They stay connected for 2 hours, and then after that, you have no users at all. They drop until there is a next game. And they want to know the things that are happening in that match exactly when they happen. It's an annoying feeling to hear somebody shouting a goal through the wall, and you don't know what's going on. And if the application has a refresh button, you hear, refresh. I want to know what's happening. OK, so these people really, really want to be updated in real time. This kind of system is a sample system, but it's very, very similar to many of those we have in our company. OK, let's start with a general design idea. what will we have there is a match process that will receive the events from that the reporter is seeing at the game. Every client will have a connection, which are those boxes on top right. And they also can use the API, which is a web server. And the match events will be stored in the database. That's because if somebody connects later, they want to know what happened before. So they will use it through the API. And the protocol, I made it like a readable protocol, so I can show you. The idea is basically you connect to through Telnet to the server. It welcomes you. You tell the server who you are. That's V2 El Brujo Halcón. And the server starts streaming events, one after the other. First, it gives you the status of the match with the players, who's winning, whatever. And then whenever there is a goal, it sends 3 lines of text indicating the data of that goal, the same for a penalty, whatever. So basically, it's a communication where you say, I'm this guy, and after that, it's all the communication happens on the other way. The server sends you events. OK, the architecture for a system like that is something like this. I will go in deeper detail on each of the processes. The first one is the client listener. If you, I guess you are familiar with the non-blocking TCP server that it was in an article on the internet a long time ago. It's a GenNB server. And it listens for TCP connections, and whenever a client comes in, it handles that connection to the client supervisor that starts a client process that has that connection and delivers the events. The clients are GenFSMs that basically receive events from the user process and delivers them through TCP to the connected clients. There is a Monkey Web server. Here it is just a box, but Monkey Web has several processes working when you start it. But to represent it, it's just a box. It's a Monkey Web server started like the usual way. It processes API call requests. Then we have this is a little forced in this sample application, but it matches what happens in real life, more robust applications, where you have, for instance, in this case, we have a process per user, because we thought a user may watch several games at the same time. So there is a process per user and a client process per game. Basically, it holds user information that it gets from the database when the process is started. And it keeps track of what matches you watched, what team you're a fan of, all that kind of stuff. And the most important part, it subscribes to a Gen event dispatcher, which is the process on the far right there. It's a Gen event dispatcher. I will talk a little bit more about that in a moment. But for each match that's being played, there is one dispatcher, and the users subscribe to that one. And finally, we have a DB process with a connection. We use the Redis just because it was there. But basically, the idea is it has a connection process that handles the TCP connection to the Redis server. OK, it seems like a properly designed system. And so we try to use it like just that. We put it in production and try to use it. And we find out that simply using Erlang to build your system is not enough to ensure that it will scale to whatever number you want. Just doing it in Erlang is not enough. You need to tweak it. You need to do it right to be able to handle the amount of users you plan to handle. To do that, we needed to test it. So what we do? We decided, what do we want to test? We wanted to see how many connections we can get, so how many users we can handle at a certain moment. Also, we need to know how many of them can connect at the same time. Remember, I told you they connect. Everybody will try to connect at the beginning of the game. So we needed to be, that C number needs to be bigger. Anybody familiar with Apache Bench will know N and C are the same thing here. And also, they need to be informed about the events as fast as they can. So that's the average response time. It's a little tricky here because as there is no response, it's not request response. The only response we have is the first event, that's for sure, because when you connect and you say your name, the server will reply with the status of the game. So we are measuring just that one. To measure these things, we create our own test client that connects through TCP and acts as a user. We use Apache Bench for the API calls, and we use. The first time we did it, I used NTOP because that's what I have at that time. But now there are a lot of other tools. Say, for instance, Bigwig. That was the SpawnFest winner, which does kind of the same thing and lets you know which processes have the longest message queue or are using most of the memory of that kind of stuff. So we started testing. Let's say the first step in every scale testing here is to establish a baseline, to know how well the system performs. To do that, we create the automated testers. We install the system on a clean machine. We run the test on the server's local network. That's important. It's like we know it's not the real deal at the end of the day, but running them in a local network means that network problems don't affect us. So what we do is we run in a local network, but we require better performance that we will actually get at the end. And basically, we test and increase the N and C values, and we test again, and we increase the values, and we test again until we find the boundaries. And the last one is important too. When we test the system with automated clients, we should never forget to have somebody else watching the system to know if it feels right. Because even if it responds to connections at the speed we want, with the amount of connections we want, maybe it's not responding properly. So we need the human eye to tell us that the system is really working while it's responding to those connections. OK, so let's make a guess. With a system designed like that on a clean Linux machine, a big machine, how many connections do you guess we will have like that, just install and run? How many people will be able to watch a game when it's happening? Who say 100,000? 100,000? 10,000? OK, no. 1,000. Just like that, 1,000.
He gets
it. Yeah.
Because I've had this exact problem.
Yeah.
The same number. Yeah, right.
Yeah, it's 1,000. And also, that ART is not a typo. It's really 26 seconds. It's a long, long time. You can have, if you are really, really fast, you can have 2 events having a penalty and a goal, and you find out when they are already playing again. So it was a really bad number. And it is a really bad number. We know we can make it better. For instance, the first thing we think is, OK, it's a machine problem. It's a machine problem. That machine is not tuned up to use to be able to run our systems. So let's tweak it. Let's make it better. Let's improve the operating system configuration because, as you know, like regular operating system like Linux, OS X are prepared for the general case. So let's make it work for our case. And also, let's improve the Erlang VM configurations. For instance, adding processes, let it run with a big number of processes, so there are no dropped clients because of that. So we tune up the file limit in Linux, the TCP connection limit, the backlog size, everything we can to let the machine know that we will be only interested in running our system there with our problems, with our configuration. And so let's bet again. How many users? I tell you, it improved. But how much?
5,000.
Almost like that. 4,000. But it's slower, as you see. It's, instead of 26 seconds, now it's 31 seconds. You can make 2 goals in that time. It's still bad, but we can improve it. We can improve it by tweaking Erlang stuff. So let's start with a kind of a configuration one. You see in this slide, we were only able to handle 4 at a time. OK, if you increase your backlog, you are telling GenTCP or Mocky Web HTTP that runs on GenTCP that you want to be able to receive more of them, queue them up, and process them later. We do that. We do that this way. Basically, when you start a GenTCP listener, you can tell it how long the backlog queue will be, and the same thing for Mocky Web HTTP start. Another thing, remember we have one connection to the database. That works, but you don't need that. You may have several connections if you handle them well. So there are some tricks in there. Some things need to be queued up. But for instance, in this particular case where all that happens is like reading and there is only one process writing, you can have all the connections you want. And in that way, you can parallelize database requests. We did it like this. We turned the internal state of our DB process from one PID, which was the Redis connection, to a list of them. And and on the init function, we start them over like with a map. But the trick is here. We go round robin the Redis connections using one at a time. And the thing that's in the middle of the yellow, of the highlighted part, I will go back to that in a while. But basically, it lets you run, it lets you process handle calls in parallel. So for each one, we use a different Redis connection. On the other hand, you have a listener. Like, we have a listener for the TCP client. Why one? That's a good question. We can have several of them. And if we need to let users know just one port, for instance, for the HTTP API, we can use Nginx or other stuff in front of us that do the round robin. So we can have several Mocky Web servers and several GenTCP listeners on our application, thus balancing the charge among them. We do that this way. When we start, we turn up our client listener into a supervisor, and it starts a list of listeners that are the same as the client listener was, one per port. And we end up with an architecture like this. Instead of one listener, we have a listener supervisor with several listeners. Instead of one web, we have a web supervisor with several web listeners. And instead of one DB connection, we have several connections. And that really improved stuff. Now we are talking. We have a small town club, but we can handle 8,000 users, 500 of them at a time, and we reduced the ART at half. So it's improvement, but we can do better. We can start with OTP behaviors. This is my favorite one. I love GenEvent. And even so, I find it has 2 or 3 things that may be better. Let's start let me tell you how GenEvent works, just so you understand the rest, the following slides. Basically, GenEvent works this way. You have a process, which is the dispatcher, that starts when you do GenEvent start. That process is basically a GenServer with several states, one per subscriber. Each of those states, anytime an event comes in, HandleEvent function is called for each of those modules that are subscribed, and when it's called, it's passed the corresponding event. So besides that, you can add a supervised handler, because those handlers are just functions, are modules with functions, nothing else. There are no process involved. But if you want to subscribe a process or something like that, you can add a supervised handler. That thing links the GenEvent dispatcher to the process that's making a call to subscribe. And it links them. That means whenever one of them goes away, the other one is notified. When you have 2, 3 subscribers, that's OK. When you have 1,000 subscribers, maybe. But when you have a really big number of subscribers, each time one of them goes down, every other subscriber is notified. That makes a lot of messages going around. Too many of them. So the solution I found was to, instead of using supervised handler, I simply add a handler, and then I monitor the dispatcher. That way, the only notification that goes through is when the dispatcher dies, which is the one that's important. I do it this way. Like, there you see add handler. It was an add sub handler before. And basically, after that, I monitor the manager. I keep a reference to that monitor. So when I get the down info from the monitoring, I know if it belongs to the dispatcher, and I do something about it. Another thing to question this behavior is like, the thing is, I told you, when an event comes in, the HandleEvent function for the different modules that are subscribed is called one at a time. GenEvent has a list of them. So if you have many subscribers, and if that HandleEvent function does a lot of work, the delivery queue goes up, like higher, higher. And also, if the events come in a faster than processing rate, the dispatcher message queue goes higher and higher and higher and higher. And events take longer and longer and longer to be distributed. So what you can do is you can add GenEvent repeaters, which are basically GenEvents themselves that are subscribed to the main dispatcher. They are many, so you distribute the work. When an event comes in, it goes through the main dispatcher, then it goes through the repeaters, and then to their subscribers. And the repeaters works in parallel. Here is a sample code of GenEvent repeater. It's basically the first function start link happens on the process that wants to start the repeater, and the other two happen in the main dispatcher code, so that you first start your own dispatcher, and then you subscribe with the repeater to the original one. Then the notification goes all the way to your clients. The notification goes from the main dispatcher to HandleEvent here, and then notifying through your dispatcher to your clients. This gets a little more complicated to explain, but basically, every repeater is started in our system on the match. So the match has several repeaters and one main dispatcher. It sends events to the dispatcher. Those events are repeated. And the user subscribes to one of the repeaters. And that got us a huge reduction in ART, like a huge one. And we've been able to handle more connections at the same time. So we are improving, but we can keep improving. We will try now with the famous GenServer. Yeah. So this one is one of those things, when you find it, it's like a revelation. You see, I was able to work for a year and a half with GenServer without knowing that function. And when I found it, I was, wow. Like, you can go out of handle call and keep the server working and reply somewhere else. It was amazing. It's amazing. Like, you don't stop, you don't block your GenServer server, and you can go like replying whenever they have a chance. It's awesome. And it's easy to do if there is one condition, your state, you need to modify your state inside the GenServer because you need to do the no reply. But for instance, in this case, the only modification was to move the Redis connections list, so we can do all the rest of the work in a spawn process there. So basically, the database GenServer is just starting processes to reply to the clients. OK, another one. It took me a long time to understand exactly what it's doing, and I think I don't. I like, OK, it works. It really, really works. But I guess it's something like Erlang gave us, the OTP guys gave us to help us. But it's like this. It goes like this. When you hibernate your process, the memory consumption for that process in the virtual machine go down. Was really low. So we do that. We can do it in handlecast, we can do it in handlecall, whatever. And that means that GenServer goes to sleep, and therefore its memory is compressed. So you can have more GenServers in the same machine using less memory. And another one, this is a hacky trick, but the thing is, sometimes, for instance, our user GenServers took a long time to initialize because they were going to the database to find the history of that user. So somewhere on the internet, I'm sorry I didn't find it again, and I don't know how to give credit for, but I found it somewhere that if you can do this. You can init, the init reply has a third tuple element, which is the timeout. If you use a 0 timeout, right after you go away from that and the GenServer is started, and whoever was calling GenServer start or start link can keep going on, that GenServer will receive a timeout. The same thing if you can use whatever number. 0 is because we wanted to initialize it right away. But if you want to initialize it like 10 seconds after that, you can. The idea is that parameter is if the server stays inactive for that many milliseconds, you will get the timeout. If you use 0, you will get that timeout immediately. That means you can move your initialization code from the init function to the handle timeout, to the handle info timeout. Therefore, whoever is calling GenServer start or start link or whatever, it's not blocked because it's blocked until the init function returns. So whoever is calling it, it's not blocked. It can keep doing stuff. In our case, it was a supervisor trying to start users. Remember, everybody connects at the same time. It had a really long queue of users that it tried to initialize. With this method, it went like tack, 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 one after the other. So So we get a big improvement with that. We can handle now 40,000 connections, 5,000 at the same time, and we reduce the ART time to a considerably good value. 25 milliseconds is really good. But as you guess, we improve it even more with one thing. This is a little trick that we were discussing that with Chad. We would love to see that inside ODB. We don't want to do this, but it's the way it is like this. You have simple one-for-one supervisors, and so you can start children. Like they are dynamic. In every supervisor, you can start a child, but in this particular case, it's used to start a lot of childs. So a lot of children, many of them. What happens? That supervisor has a list in its state. So if you have a lot of children, each time you want to start one of those, the memory of the supervisor increases, and it takes longer. It takes longer and longer and longer. So again, the same trick as before. You use a supervisor hierarchy. We call those in the middle, we call them managers. And basically, in this case, again, I think the user supervisor has a group of supervisors as children. And whenever you want to start a user, you start it on one of those children. We couldn't use round robin because we have no access to the internal state of the supervisor unless we ask for it. So we use a random. You just pick a random one. It works very well. And so the architecture turns out like this. Instead of a client supervisor with a lot of clients, you have a client supervisor with several managers. Each one has a piece of the client processes we have. The same thing with the user supervisor. And it turns out we can handle now 50,000 users, 8,000 of them at a time. And that soccer stadium is from one of the most important soccer teams in Argentina. We can handle more people that stadium can fit. So the last list of tricks. This one is a particular one. There is choosing a login system is very important. It's like those things where you can screw things really, really bad or do it really good. What you need to do is you need to choose a login system that informs you of the relevant things when you are in production, but doesn't get in the middle of your scalability purposes. When we did when I built this system, I did a new lagger. So in Akka, we developed our own login system called elog. It's good, but now I recommend lagger. Lagger is a good one. And basically, the idea is to be able to know, to be alerted about errors, but to keep the login information the lower possible. Another trick. This is complicated for me to explain, but I will do my best. The idea is, for instance, we have a dispatcher on where users need to subscribe. So to find that dispatcher that was started by a match process, they needed to ask the match process which dispatcher they needed to subscribe. It was a handle call. Like when a user came in, it asked the match, OK, I want to watch that match. What subscriber? Where is the subscriber? Where is the dispatcher? The match goes, find its dispatcher, returns, and the user then subscribes. To avoid that round trip, we can register the dispatcher with a proper name. It's a naming convention. So we know where that is beforehand without going to the match. So the user can simply subscribe to that process. Like this. Instead of a GenServer call on the first function, we just do some magic to get the dispatcher name. And when we started on init in the match process, we registered it that way. Now we can handle the same amount of users, the same connections at the time, but we improved the speed of the ART. And this is where the trick I told you at the first time makes sense. It's not that every event is faster. It's just the first event. It takes smaller time to retrieve the first event because we don't need that handle call in the middle. OK, so the final part, we have a system that scales in one node. It works pretty well. Let's do what we know we can do with Erlang, which is adding some other nodes. Again, as first, I think like, OK, just start another node, start the application in it, and everything works. Well, not the case. Because there are several things you need to consider. Maybe, for instance, in our case, we don't want several match processes listening to the reporter, because if that way, the reporter must tell the first one, the second one, the other one. It's complicated. We don't want to write the events several times in the database either. We want to write them once. So in this simple stage, I'm not talking about a lot of complicated stuff like nodes going down, nodes going up, all that other things that are messy with it. In just the simplest possible case, just to get it running, we needed to prepare the system. We needed to decide which processes we needed to register locally, globally, how they need to connect, how they need to communicate. And we came with this. Basically, we connected the match processes using PG2, and we split the database in two. One unique in the system, like globally registered DB writer, and one DB reader per node. Then we started there is the resulting architecture. Basically, the only change it's noticed is that divided database structure. And then we started 4 nodes in the same machine, connected into them. We were able to handle 100,000 users, 32,000 of them at a time, with the same ART. That means a bigger stadium. That one is for Barcelona's stadium. OK, let's recap. We started with 1,000 users, 4 at a time, 26 seconds to get their first message. And with small improvements, one tiny step at a time, and nothing so drastical, like we didn't redesign the whole application, nothing like that. We moved to 100,000 users, 32,000 at a time, and with an average response time of 10 milliseconds, which is 100 times better for the amount of users, 8,000 times better for the concurrency value, and 2,600, yeah, English, 2,600 times better to get the first event. And I should remind you, this is an iterative process. Iterative in the sense that it goes one step at a time. We will improve it slowly, but also iterative in the sense that it gets better with every system you scale, because you learn new tricks, new stuff to do. And for us, it was really useful. That story I told you about like a fictional system, which is real. You can download it from GitHub, but I mean, it's not a real life system, happened to us in a real life system, in more than one, like for at least 2 production systems. And the second one was a fast process. Like, we didn't even notice. For the first one, it was like a month of work. And it gets better and better and better. OK, that's it. Questions? Oh, where? Yeah.
Maybe I missed it, but you said that when you increased the number of nodes on the machine from 1 to 4, you got a pretty significant increase again. Do you know why you got that increase?
Not really. I guess it's because, for instance, we listened to 4 times the ports that we were listening before. We had, I don't know, we had 4 times the connections to the database. We increased the same things we were increasing before. We increased them again, all those things.
But I think when we've done that, I think my theory is it's CPU scheduler. That the CPU scheduler running 4 Erlang nodes is better than 1 Erlang node with a lot more processes.
So it's the scalability of the Erlang schedulers.
Yeah. I mean, I don't know if you agree with that.
Maybe, yeah. Mahesh?
This is actually more a comment, but I suspect most everybody's been through exactly the same thing. I know I've been through it twice. So twice says something about OTP and what needs to be done at a very basic level, or tool sets or something.
Yeah, there are things that we were considering, like, for instance, the gen event add supervisor handler. It's something that maybe fixed at OTP level. The supervisor hierarchy is something that we would like to have, like, from the OTP itself. Yeah, there are many things we improved because we needed, but it will be convenient if they are already on the provided OTP gen event behaviors. Yeah.
The talk after this one in Crystal is by this guy Garrett Smith, and he wrote basically a library called E2. And part of what it does is it takes the patterns like the 0 timeout, and it makes them part of the not a pattern, but I mean you have to check out E2. But he tries to take those things and sort of improve OTP by making it just part of it, not something you have to find later. But
Right, I was talking to him about that. I do think these patterns, or patterns like these, we just need much wider dissemination and distribution about this for people that actually care about scale.
I will definitely go to that to that talk. Yeah.
I think we're about out of time unless there's one more short question. All right, thanks, Fernando.
Thank you very much.
That's a really good talk. Thank you.
Thank you.